Hi and welcome back to Properties and Structures of Matter, and today we're looking at bonding spectrum. So we've already spoken before about the different types of bonds that we have, and that we have our non-polar covalent bonds between about 0 and 0.4, polar covalent bonds between 0.4 and, as we said in our last video, about 1.5 to 1.7. It does depend on what book you go to, and different scientists have their own little opinions, so that line is a little bit blurred. In this case, in this diagram, it's got it at 2, and an ionic bond, and it forms anywhere greater than that. So coming back again to our continuum, 0 all the way up to greater than 2 at least, but let's call it 4. And down this end, we have got our pure covalent. Up here, we've got our ionic. And at about this area here is where we say have our polar covalent bond changing over into our ionic, about 1.5-ish. So, as we've said before, it's a spectrum, and there's a range of where the bonding occurs, from the 0 being pure covalent up to the maximum, which is our ionic bond. And so there's no one defining point. It's a bit of a blurred line there. So again, there's no one definitive point that it changes from being this, but rather a transition into. So when we are looking here, we're looking at sometimes our polar bonds. So sometimes what happens with our polar bonds is one of the atoms there has a greater force, a greater attraction of the electrons than the other. So you can see here in the polar covalent bond we have here, there's not an equal sharing of those electrons there. One of them has a greater pull than the other. With our ionic bond, as we've spoken about before, it's a complete transfer, so that one electron is plucked or transferred from one atom to the other, and they are then forming their own electron clouds. With our non-polar covalent bond, it is an even sharing, as we spoke about before with chlorine, 3.16 minus 3.16 giving a 0. There's no one has a greater affinity for the electrons. They both have the same pull, so that they share them equally. So with our non-polar covalent bond, like I said before, those electrons are shared evenly, whereas our polar covalent bond has that greater affinity. So when one of them has that greater affinity for the electrons will spend more time in and around that atom than it will the other. So that's then called a polar bond. So let's just have a look at an example. If we look at the example of water, so we have an oxygen, a hydrogen, and another hydrogen here. If we look at the electronegativity here, the electronegativity of oxygen is greater than the electronegativity of hydrogen here. So what our electrons are going to do is they're going to spend more time in the region of oxygen than they are in the region of these hydrogens here. So if the electrons are spending more time in and around this oxygen, it is going to become slightly negative. So even though they're sharing those electrons, it has a slight negative, and we use the symbol delta for that slight negative, a delta negative. So if the electrons are spending more time in this region, they're going to have a slightly negative charge, which is going to make our hydrogens here have a slight positive charge. Okay, and that's what we call a polar covalent bond. The electrons are spending more time in this side than the other, and there is a slight difference in that charge there. Now, we have different things called polar bonds and polar molecules, and they are slightly different. So in this case here, these are polar bonds. Okay, but there is a difference between polar bonds and our polar molecules. So if we actually have a look at the polarity of a molecule, what we actually have is we are looking at then what is the difference. I've got a polar negative up there, but I've got a delta negative up there, and I've got two delta positives up this side. So what can happen sometimes is the negative can cancel out the positive, and if that occurs, then it will be nonpolar. But if one of them has a higher value, a higher delta value, then they won't cancel each other out, and what's happening then is we get what's considered a polar molecule as well as a polar bond. So to do that, we need to then look at the values of those delta, the delta values, to see whether do they cancel each other out, or if they don't. If they do, they're nonpolar. If they don't, they are polar. But we will look at this a little bit further along in the course. Talk to you soon. Bye.